this video, we will take a closer look at Gibbs Free Energy and how we can use the equation to determine whether a biochemical reaction occurs or not. In a previous video, we defined that the universe conserves energy and always moves towards an increased entropy state, or a state of increased randomness. To achieve this, biochemical reactions must move towards lower energy states, releasing energy and thereby increasing disorder or randomness in the system. If we revisit the example of the conformation of ethane with the methyl groups rotating around the central carbon bond, moving from the eclipsed to the staggered conformation decreases potential energy and therefore increases entropy. The staggered conformation is therefore energetically favourable and more stable. Gibbs free energy is defined as the usable energy in a system, or the energy that is available to do work. If we think of the change in free energy, or delta G, as the difference between the free energy of the products and reactants of a biochemical reaction, then we can determine whether a reaction will occur spontaneously or not. If delta G is less than 0 or negative, then the reaction can proceed spontaneously as it releases energy or is exothermic. If delta G is greater than 0 or positive, then the reaction cannot proceed spontaneously as it is endothermic and requires energy to be provided to the system. A system that is high in free energy is unstable and will spontaneously move towards a more stable state. Let's look at a bottle of Coke as an example. The gas in the Coke is under pressure, and when you open the bottle, that pressure is released and gas escapes and becomes more stable. Now, if you take the bottle of Coke and shake it, then you are increasing the free energy in the system. When you open the bottle now, the result is much more explosive. Higher free energy was unstable, and the system tries to get to a lower energy state as quickly as possible. The Gibbs free energy equation is written as G equals H minus Ts, where G is the Gibbs free energy, H is the enthalpy or total energy contained within the system, T is the temperature in degrees Kelvin, and S is the entropy or randomness of the system. Perhaps a more useful classification, though, is delta G equals delta H minus T delta S to define the change in free energy in a system at a constant temperature. Using this definition, we can classify reactions into 4 distinct scenarios. Remember that for a reaction to proceed, delta G needs to be negative, i.e. the product of T times delta S needs to be larger than delta H. If the change in enthalpy is less than the change in entropy, then delta H is lower than T delta S, i.e. the energy contained within the chemical bonds is less than the entropy adjusted for the temperature, and the reaction proceeds spontaneously. If the change in both enthalpy and entropy are negative, then a reaction can only occur at low temperatures. If both enthalpy and entropy changes are positive, then the reaction can only occur at higher temperatures. And finally, if the change in enthalpy is higher than the change in entropy, the reaction cannot occur at all. If we think about the bottle of Coke again, the release of gas when the bottle is opened was spontaneous. But there is no way of getting the pressure back into the system without adding energy back into that system yourself. So the repressurization of Coke is not possible, it's not spontaneous, as you are forcing the system from a stable to a non-stable state. 2 other aspects that we need to consider at this point are the directionality of a reaction and the equilibrium constant, as these also characterize biochemical reactions. The first thing to define is equilibrium. Consider a reversible reaction, one that can proceed in either direction, where the substrate S and the product P are interconvertible. At equilibrium, there is no net change in the concentrations of S or P. Importantly, this does not mean that the concentrations are equal, just that the rate of interconversion is steady. The rate of S and P formation are the same. What it does mean is that the ratio of the concentration of the product at equilibrium divided by the concentration of the substrate at equilibrium is constant. We call this the equilibrium constant. If we look at a reversible reaction, where A plus B gives C plus D, then the equilibrium constant is given as the ratio of the concentrations of C times D at equilibrium over the concentrations of A times B at equilibrium. If the equilibrium constant is greater than 1, then C and D are more abundant at equilibrium. If A and B are more abundant at equilibrium, then the equilibrium constant is less than 1. And if the concentration of A and B exactly equals C and D, then the equilibrium constant will be equal to 1. So what about directionality? Almost all biochemical reactions are reversible. For example, deoxyhemoglobin binds to oxygen to form oxyhemoglobin, and oxygen can dissociate from oxyhemoglobin to form oxygen and deoxyhemoglobin. In order to determine which direction a reaction proceeds, we need to introduce a concept called the Chatelier principle, which states that when a dynamic equilibrium, as shown here, is disturbed by a change in concentration of one reagent, the equilibrium shifts to bring the reaction back to equilibrium. The graph on the right shows the free energy of the reaction as it proceeds from left to right. For simplicity, I'm focusing on oxygen here and not showing deoxyhemoglobin. As we move from left to right, more oxygen is being bound to form oxyhemoglobin, until at the far right, all the oxygen is bound as oxyhemoglobin. At equilibrium, the lowest free energy is achieved, and the ratio of oxygen and oxyhemoglobin equals the equilibrium constant. As we move to the left of the graph, the concentration of oxygen is higher than at equilibrium, and as such the spontaneous reaction with a negative delta G is to the right, and oxygen will bind with deoxyhemoglobin to form oxyhemoglobin, driving the forward reaction. At the other extreme, we have a higher concentration of oxyhemoglobin than at equilibrium. This time, the spontaneous reaction with a negative delta G is to the left, and so oxygen dissociates, driving the reverse reaction until equilibrium is reached. At equilibrium, there is no net change in the concentration of oxygen and oxyhemoglobin. So what is the link between free energy and the equilibrium constant? Glycolysis is a series of chemical reactions that allow cells to produce energy from glucose. One of the very early steps is the conversion of glucose 6-phosphate, G6P, to fructose 6-phosphate, F6P. The equilibrium constant for this reversible reaction can be determined experimentally as 0.51, meaning that the concentration of glucose 6-phosphate is almost twice that of fructose 6-phosphate at equilibrium. Delta G0 prime is defined as the change in free energy under standard conditions. These conditions have been defined as the temperature being 25 degrees Celsius or 298 degrees Kelvin. If gases are involved, they are at a pressure of 1 atmosphere, and all reactants and products are at an initial concentration of 1 molar. We can calculate delta G0 prime using the equation delta G0 prime equals minus RT, natural log of the equilibrium constant, where R is the gas constant and T is the temperature in kelvins, which we've defined as 298 degrees. Working through this calculation gives us a positive value of delta G0 prime, which means that the reaction is not spontaneous, and therefore should not occur in our cells. But we know that this reaction does occur. So how do we explain this? Well, delta G0 prime is calculated under standard conditions, whereas what we are really interested in as biochemists is the physiological conditions found in our cells. The actual change in free energy is calculated using the equation delta G equals delta G0 prime plus RT natural log of K, where K takes into account the ratio of glucose 6-phosphate and fructose 6-phosphate under physiological conditions. If we run the calculation again, we find that in fact delta G is negative, and therefore the reaction occurs spontaneously. This highlights an important consideration when talking about biochemical reactions in our body, which are mainly prevented from reaching equilibrium due to the addition of more substrate or the removal of products. In this video, we have looked at how biochemical reactions approach equilibrium and linked this to free energy as the driving force for biochemical reactions. We also showed that the change of free energy can be calculated to predict the spontaneity of a reaction, but also highlighting the need to consider the physiological conditions of that reaction. I hope you found this video useful. If you did, then please give it a thumbs up. Consider subscribing to the channel and click the bell icon so that you'll be notified of any new videos when they are released. If you have any questions about the content covered in this video, then please post them in the comments below and I'll try to get back to you as soon as possible. I hope to see you in the next video.